So with that, let's get started. I'm sure all of you know this. Building things at scale is hard. And your customers demand exacting performance, predictable performance, and some of the applications which you build on DynamoDB are truly impressive scale. The thing which we find is that the applications you build are so complex. DynamoDB is a tool. It is much easier for you to build these applications if you know how DynamoDB is built, but also if we're able to tell you some of the things we learned along the way. So the point of this talk is to share some of those learnings. My name is Amrith. I'm a senior principal engineer with the DynamoDB team. I've been here about 4.5 years. And this entire time at AWS, I've been in the DynamoDB team. So what we're going to be talking about is how we built DynamoDB at scale. And we want to share with you some of the things we learned, because they will be applicable in the applications you're building. And hopefully, you don't make the same mistakes which we did along the way. So there's another part of it. Like every engineer, I'm really proud of the things which my team has built. So I would like to show those off as well. The first part of this presentation is going to be a very quick, the nickel tour of the DynamoDB architecture before we dive into 3 specific topics. The first one, memds, which is an internal data store, which we use for partition lookup. The second is we'll talk about things related to a new feature we launched 2 weeks ago called warm throughput. And then we'll talk about synchronous global tables, or strongly consistent global tables. Okay. So DynamoDB, in addition to all the things in yellow up top, the reason why people use DynamoDB is because you want to build applications which give you predictable response times at any scale. This is what your customers ask you for. We're building the database which does the exact same thing. So I'm going to repeat these 3 things over and over during this talk. Predictable, low latency at any scale. That's what we're all about. And building applications at scale which give you predictable latency is hard. How we did it is what this talk is about. So if you've used DynamoDB for a while, you know that all data in DynamoDB is stored in tables or indexes. Throughout this talk, when I talk about tables, it equally applies to indexes. Internally, we store indexes just the same way we store tables, so I'll keep it easy. I'll just talk about tables. When you create a table, we ask you for a table name, and we ask you how you want to distribute the data in that table. We horizontally scale, so what's the distribution? So here's an example. I've got a user's login, a name, and some other information, whatever that information happens to be. And I've determined that login is a primary key. In the traditional relational database sense, it's unique and it's not null. So I say distribute the data based on that. Now, what we do internally is we use the login key to decide how we distribute it. Quick aside, I've spent 35 years working with databases, mostly building them, for a brief period using them. My fingers type SQL a whole lot better than they type the AWS command line. So when I started working in this team, not having a CLI like the MySQL CLI kind of put a cramp in my style. So I built this thing for myself. It's a DynamoDB shell. It gives you a SQL-ish kind of interface. It's open source. You can download it. You can use it. It's available on Homebrew if you want to. So you'll see these things which look like SQL. DynamoDB is not becoming a SQL database, right? This is just easy for me to show. It's easy to read and say, I want to create a table. I want the primary key to be login. That's it. So if you want to use DynamoDB shell, there it is. When you create a table that way, and I'll show you some other cool things with DynamoDB shell. I did tell you engineers like to show off, right? Yeah, okay. So I have a table sorted by the login on the left. Compute the hash. Now, this is not the real AWS, this is not the real DynamoDB hash. This is just a generic MD5. Sort the data by the hash. And then we divide it into a couple of chunks. Here I said 4 partitions. So that data, these 4 partitions worth of data, are stored on storage nodes. Storage nodes are hosts which we provision, the DynamoDB service provisions, and we put your data on those storage nodes. Now, storing 1 copy of data is not really good. We continuously deploy software to hosts. At the scale at which we operate, building things at scale is hard. At the scale at which we operate, hosts fail constantly. 1 copy of your data is never a good idea, so we keep 3. Right now, we keep 3. Number may change in the future. And we store the 3 in 3 different AZs. So an AZ is a fault containment zone. AZs never share fate. So if you're building your application and you want high availability, that's a good concept for you to use as well. Have your application distributed in multiple AZs. Now, having said that the data is in 3 AZs, we take care of the replication for you. You don't have to do any of this. You created a table. You said what the primary key was. The rest is ours. Okay. Having decided that we're going to replicate all of this data, we do one further thing. One replica in each partition is defined to be a leader. A leader is that replica which will serve writes, and that is the replica which will serve strongly consistent reads. The leader will always have the most recent information. When you do a write, the leader will serve the write, and the write is acknowledged as long as one other AZ acknowledges the write. The third one, may take a couple of milliseconds. All right. So now that we've done that, we said we have a partition. We try to keep a partition about 10 gigabytes in size. And the reason why we chose this particular size is there's a lot of operations we do on tables, and we want to do them in parallel. What are the 3 things DynamoDB is about? Predictable, low latency at any scale. You have a table which is a terabyte. Somebody else has got a table which is 200 terabytes. If we have it all in one partition, doing any operation to recover that table could take a variable amount of time. We want predictable amounts of time. 10 gigabytes is a nice chunk. If a partition or a replica fails, all we're doing is recovering 10 gig worth of data. Simple. So you load data into a partition or into a table, and one of the partitions starts to reach that 10 gig size. We split the partition. All done for you. You don't have to bother about it. A partition is effectively a contiguous range of key hashes. We want to split this partition. We just drew a line somewhere in the middle, and we said, OK, now you have 2 partitions. So you had P0, 1, 2, and 3. Now you have 4 and 5, and 3 ceases to exist. So this ceases to exist, and now you have P4 and P5. OK. Everybody with me so far? All right. So DynamoDB is serverless, which means you don't have to provision any servers. We do that for you. So we have tens of thousands of servers in each region to serve DynamoDB. And here is one partition of one table. 3 replicas, 1 in each AZ. Now, here's the part where I want you to look to the person to your right and the person to your left. Do you by any chance know them? No. You probably want to, because this infrastructure is shared by everybody in DynamoDB. So if the 2 of you use DynamoDB, your partitions and replicas are probably sharing a host somewhere. And since this is common infrastructure, we don't want any individual tenant to monopolize that host. So on a per partition basis, we have some limits. Right now, the limits are you can't do more than 3,000 reads per second or 1,000 writes per second. That could change. If your partition goes over 10 gig, we'll split it. If you consistently drive traffic over 3,000 and 1,000, we could split it. Split for size, split for heap. All done for you. You don't have to do any of this. So be nice to the person next to you because they might share a storage node with you. So that's the infrastructure we operate for you on the storage side. Now, we want predictable, low latency at any scale. We can't have your applications directly connecting to all these storage nodes. So the way in which it actually works is your application, which typically talks to us through the SDK. Some of you use a low-level API, but we'll just talk you use the SDK. You resolve the regional endpoint for DynamoDB in whatever region you happen to be operating. That will connect you to one of several load balancers. We have tens of thousands of load balancers in every region. Also, we have those divided into AZs. Behind a load balancer is a fleet of request routers. So when you make a connection from your application, your SSL termination is going to be on a request router somewhere. When you send a request to DynamoDB, the first thing we do is we authenticate, make sure your SIG-v4 signature is correct, make sure that the operation you're trying to perform is one which has been authorized. Do you have access to the table which you're attempting to read or write from, or the index as the case may be? Earlier this year, we launched resource-based policies. For those of you who've used DynamoDB for a while, we only supported identity-based policies in the past. Resource-based policies are verified on each and every request. Now, we have over 1 million customers. Some customers send over 1 billion requests an hour. Some of those customers are in this room. Each and every request needs to be authenticated, authorized. We then need to make sure that whatever it is you're doing is within the limits which you've set for that table. If it's a provision mode table, are you overdriving that table? Do you have account level limits which you don't want to go over? We have to do that. Once we're done with all of that, we determine where your data is stored, and we forward your request to a storage node. So it started here, your application came to a load balancer, request router, down to a storage node. That's where your data actually is. Now, whether you like it or not, every item in DynamoDB is encrypted. If you provide us a key, we will use your key. Otherwise, we have keys. There is no data which is stored in DynamoDB which is not encrypted. So your request made its way to a storage node where, again, since you share the storage node with the person to your left or the person to your right, we make sure that you're not overdriving that particular storage node. And we respond. But we do this hundreds of millions of times a second. That's one of the things which we've noticed that people do with applications at scale. A shopping cart application does the same thing over and over again. It puts stuff in a cart, takes them out of a cart. When you check out, it does the same thing. If you're uploading pictures, your application does the same thing over and over again. And that's what we optimize for. And that's the thing which gives you predictability. Okay. So we talked about your request making its way to a load balancer and then to a request router. And I've colored these arrows red and green for a reason. When you make this request, a request can be sent to any load balancer to any request router, because all the request routers, they're stateless. But a request router has to send your request to a specific storage node, because that's where your data actually is. So the thing with the request router has to do is authenticate, authorize, make sure you're within your limits, make sure that resource policies are complied with and all that, and then it's got to figure out where your data is. Hundreds of millions of times a second. So one of the things which we haven't talked a lot about in our documentation and so on is how we actually go about doing that. So that's going to be the first part of this presentation. So let's quickly recap what we've done so far. We're all about giving you predictable, low latency at any scale. We do this through horizontal partitioning. We have to make sure that you comply with whatever rate limits there are on the shared infrastructure and whatever you've set for your table as provision mode limits or as on-demand table limits. But at all time, we ensure security, durability, and availability. As far as we're concerned, those are non-negotiable. We will make sure your data is secured. We will make sure that when you write the data, it is stored securely onto 2 storage nodes before we say yes. And we will make sure that your data is always available to you. I said I've been in the DynamoDB team for a little over 4 years. DynamoDB has been around for a little over 12. In this entire period of time, the total number of planned downtimes we've had is 0. Our intention is to have the database up and running 100% of the time because that's what your customers demand of you and the applications you're building. So secure, durable, available, predictable latency at any scale. That's what we're about. So let's switch gears and say, you're a request router. You received a request. You need to send that request to a storage node. Now, how do you go about doing that? So let's take a specific example of this. Here it says get item or put item. And here the partition key was Jorge, or the second one is Richard. Now, I told you that a partition is a contiguous range of key hashes. So what's the first thing we do? We compute the key hash. So what is the hash of Jorge? Well, it's this big D99 whatever string. And we know that for the table, this is the login table, after the split, there's now P0, 1, 2, 4, and 5. And the number we're looking for, D99 whatever, is down here. I've dry run this presentation a couple of times, and I know that this entire description took a couple of seconds. We need to give you predictable responses in single-digit milliseconds. We need to do this lookup hundreds of millions of times a second. But we got to do that in tens of microseconds, predictably. Because if we can't do this in tens of microseconds, there's no way we can get you your data in a single-digit millisecond. So the first part of this talk is going to be MemDS, which is a system we built to do exactly this. So to give you an idea of the scale at which we're operating, the traffic we serve today, there's hundreds of tables over 200 terabytes apiece. We have 1 million customers. Some of them drive a half a million RPS. And there are tens of thousands of storage nodes. There's tens of thousands of request routers in every single region. And these are on tables which are being continuously created, deleted, split, and we'll talk about moves in a second. How are you going to keep track of where this data is and produce an answer in tens of microseconds? So clearly we have some kind of metadata store, so let's see if this works. So you got here all the request routers on the left. You got all the storage nodes on the right. They have little disks there. That's where your actual data is stored. And there's some partition metadata, which is in a database of its own. And this partition metadata database has disks and it has persistence. And creating and dropping tables comes through the control plane, so we'll talk about that. Does this work? Anybody see problems with this? Remember, you're serving hundreds of millions of requests a second here. A request comes in, it's authenticated, authorized. Where's Jorge? Oh, let's go read it here. If you get 100 million requests per second, this is serving 100 million requests per second. What kind of database do you think this is going to be? Well, this is going to be bigger than DynamoDB itself. That's a little bit of a problem. So clearly this doesn't work. And oh, by the way, tables are being created and dropped continuously. Partitions are being split. These are going to go and try and update that table. Well, what happens when you try to update a table? You have to hold some kind of lock in that. You try to hold a lock here, then the requester is going to be locked out. So you're going to have unpredictable latency. Yeah, clearly this doesn't work. So it has all kinds of problems. So smart engineers look at this and say, this is easy. Let's just put a cache in front of it, right? That's the first thing every engineer says. Put a cache in front of it. Does this work? Nod if you think it works. Shake your head if you think it doesn't. Oh, I can't see too well. Okay. I see some people shaking their heads. Well, this doesn't work either for a couple of reasons. So you make a request, it comes to the request router, it's not in the cache. Well, you're going to go over here. So this thing is going to have to serve that. But you have the same problem with this the storage node's trying to lock and all this stuff. Okay. But once you get it in cache, that's great. You have a connection, your connection endpoint is to a request router. You're going to keep making requests to the same request router. You're going to keep looking up something in the logins table. If not Jorge, somebody else. So the cache is going to say where all the partitions are. Good. Then along comes one of our engineers and says, I want to deploy software to this request router. Takes it down for about 20 seconds. Now the cache is gone. Every time we do software deployments, we're going to go back here and try and read it. So now you have unpredictable latencies. What happens if for some reason an entire AZ happens to go away? Network isolated. All your traffic has to fail over to another place. You get another bunch of problems. This whole system is kind of on a hairy edge. So this didn't work either. So we designed this, we drew it on a whiteboard and said, yeah, no. So then we said we have to make it a little bit more complicated. So we came up with this design. Now here, the storage nodes have disks. Notice that there's this thing in the middle which is called memds, has no disks. It's a completely in-memory data structure. And memds is a parallel database unto itself. There are hundreds of nodes which have partition metadata, and they're all almost identical, within a couple of microseconds of each other. Then we did a couple of other things. Now, if you look at the previous slide, we talked about the storage nodes updating the partition metadata whenever they did a split or a move. Yeah, we don't want all that, so we added this new component called a partition publisher. And I'm going to ask you the question, does this work? But please don't say it doesn't, because this is what you're actually running today. If you think it doesn't work, let me know after, because we have to talk about that. So the architecture looks something like this. memds has no storage. It's all in memory. Hundreds of nodes, almost synchronized data. Almost, not exactly. A partition publisher whose job is to continuously poll all the storage nodes. Okay, storage node, what do you have? I got these partitions for this table, these key ranges, and so on. What happens when we split? We'll see that in more detail, but there's only a polling operation here. One of the things which is synchronous, however, is a person comes along, creates a table. Okay? You make the create table API call, you pull the status, you wait for it to be created, it's now active. What's the first thing you're probably going to do? Try and write an item to that table. So a request shows up at a request router. If memds doesn't know about it, okay, we got a problem. So the control plane will explicitly publish. And that starts the process rolling. So we have a cache, we have storage nodes, we have polling. I think we're kind of at the point where this might work, so let's take a look at it some more. So let's talk about new table creation. We said person comes to the control plane, makes a create table call. As part of the create table call, we have this publish to memds step, where we will write it to all the hundreds of memds nodes. Therefore, partition metadata is available. In parallel, we go and tell the storage nodes which are going to host partitions for that table. This is the table you're going to be hosting partitions for. Great. Nothing is put into these caches at this point. Fine. A storage node decides it wants to do a partition split, or, again, building at scale is hard. We've got tens of thousands of storage nodes. If you created a table in DynamoDB at, say, the beginning of this year, 2024, there is a very good chance that the partitions for that table are not on the same storage nodes where they started off. The host has probably been retired. The partition's probably split. It's probably been moved for whatever reason. Moves happen continuously. So a partition is being split or moved. One of the storage nodes talks to another storage node and says, okay, we're part of this split or move operation, so now the partition's moved. Well, nobody's updating memds in the process. At some point, the partition publisher will come along, it will do a poll, and it'll figure out what's going on. So At this point, we've got a situation where MemDS has a view of the data, which is potentially stale. The storage nodes are the ones which really know what they have. So a storage node's got some number of partitions on it. That's the eventual system of record. So this is an eventually consistent copy on top of which we've got a cache. But in order to distinguish between the partition before the move and after the move, we put version numbers on that. So we create a table, the version number is probably 1, you move a partition. The new partition here has probably got a version of 2. When it was here, it was version 1, now it's version 2. Okay, let's see how that works. So we start with a request. Request router says, get me the item for Jorge, and oh, by the way, I looked in my cache, and I have the version of data from the last request, which was at version 20. Okay. So it goes over, version 20 says Jorge has to be here. What it didn't know was since it got this data, the partition had moved. So the storage node knows, I don't have that data anymore. It says, I'm sorry, I don't have it. I'm at version 21, and maybe the place you need to go is here. Okay. The request router updates its local cache. Notice, nobody has touched MemDS yet. The request router updates its local cache, goes to the new storage node and says, could I have Jorge, please? I'm at version 21. Storage node replies with data. Your request is served. Over. Now this request router goes and tells MemDS, you probably want to go get version 21. The MemDS will tell the partition publisher, which will go get the data. This eventually consistent data set will get updated. Okay. So the way this all hangs together is something like this. You've got a control plane. When you create a table, it pushes data to MemDS, because when you create a table, the very first thing which comes after, which might be before the partition publisher goes and does anything, is to write to the table. So MemDS needs to know the table exists, so we do that. Beyond that, MemDS has no persistent storage. Partition publisher scans all the storage nodes in the region continuously and publishes it to MemDS. So that is the system of record. That's the authoritative store. The storage node knows what it has. Partition publisher reads it eventually consistently to MemDS, and you've got versioning, and you've got an eventually consistent cache. Most of the time, your request gets served out of this cache. The first time you make a request to a table which nobody knows about, maybe it'll take a little bit longer. That's the tail latency you see. But we've built this complete set of eventually consistent stores because we want to avoid things like locking. And we've built versioning into it to make sure that if there is stale data, we can detect it and we can do something about it. So I've gone through this kind of quickly. If you're like me and you want to get into the weeds on this, we actually published a paper about this at ACM last year. That's a QR code for the paper, and it goes into a lot of detail about this. So this is the basic architecture for MemDS. But I did tell you that building at scale is hard, and you want predictability. So there's a couple more things which we talk about now. When you want predictable latency from a database, a strongly suggested pattern is to hedge your request. Make 2 connections to the database, make 2 requests, and use the first set of results. So if you make a request and the distribution of response times is some bell curve, and you happen to be one of those, or you happen to serve the request which is in that P99 or higher latency, by sending 2 requests, the odds that both of them will be slow is pretty low. So you want predictable response times, make 2 requests, and this is a normal pattern. It's called hedging. We didn't invent this. This was invented by the folks at Google. The paper is by, I think, it's called Tail at Scale. I don't remember the year it was published, but Dean and Barrows, I believe it was, Dean and Barroso wrote this paper. Useful pattern for you to use when you're building your applications, make hedge requests. One of the things we've seen some customers do when they want predictable low latencies is they go play with timeouts. Very dangerous thing to do. Happy to talk to you about why. Hedge instead, it's much safer. All right. Another thing we want to do, and this is a pattern we use in many, many places in DynamoDB, is constant work. You want your system to always be running in the same steady state, or as close to the steady state as possible. Consider the case of a cache system. So I highlighted a request router in a cache. Let's assume this cache has got a very good cache hit ratio. If your memds system behind it only serves the cache misses, and something happens and you deploy software in AZ or something like that and a whole bunch of caches get stale, this memds system will get overloaded and fall over. You never want something like that. So what we do, you make a request router looks in its cache, does a cache lookup, has a cache hit. It uses the value which is in its cache. It serves your request. It goes to that storage node, gets the data, whatever. But then it makes 2 requests to 2 memds servers, always and every time. So if the front door traffic on the request router is hundreds of millions of requests per second, memds is normally serving 200s of millions of requests per second at its normal CPU utilization. So let's assume that all these caches were to fail. memds wouldn't bat an eyelid. It'll keep serving traffic. We did say secure, durable, and available. This is how you build availability. This might seem like overkill, but this is the cost of building a highly available system. When you build a cache, think about hedging and think about constant work. That's something which we learned. And we've talked about partition metadata caches, but we also use caches for authentication and authorization information. If you've used our resource policy implementation, you will know that when you change a resource policy, it may take some number of minutes for the new policy to take effect. You know why? Because the control plane cannot publish to tens of thousands of request routers synchronously. There's a TTL on those caches. It ages out in a couple of minutes. The new policies are loaded. When possible, at scale, build systems which can embrace eventual consistency. If you build systems which are synchronous, it becomes really hard. So we've got caches for multiple things, permissions, and we use TTL to expire that data. So at the beginning of the presentation, I said, I'll tell you how we built it, but there are also takeaways for you for the applications which you build. Wherever you can, try to keep your caches eventually consistent, and where possible, embrace it and use it to your advantage. If it's not possible, then build synchronous caching. It's much harder, and it introduces variability in performance. Recognize that and try and avoid it. But knowing that request routers do a lot of caching, a good thing for you to do, I have to add this. Engineers think adding caches is easy. Very dangerous. Careful with it. If you have long-lived connections to request routers as you do, there's a benefit. You don't do TLS authentication, you don't do TLS handshakes every time, but you also get the benefit of the caches we have on the request router. Even if you're building an application which is using lambdas, try and use a pattern which will keep a long-lived connection to DynamoDB. It's a significant benefit to you. There's a lot of times when you get calls from customers and they say the latency is unacceptable. And we go and debug it, and they make a connection, they send a request, they close the connection. Which means not only are you doing a TLS handshake every time, but your request may be going to a completely different request router, which has no caches for your tables. Try to use long-lived connections wherever you can. If you want predictable latencies, consider hedging. And wherever you build systems at scale, try to keep to constant work. systems which are not running at constant load have unpredictable failure patterns, something which we've learned. So hopefully this will help you. So how are we doing on time? Okay, pretty good. So one of the things which I spend a lot of my time doing is speaking with customers. And since we have a limit on the amount of traffic we allow per partition, one of the things which customers have come to us and said is, and customers have asked this many times, is if a partition can do 1,000 writes and 3,000 reads, which are the numbers today, I want to know how many partitions there are, because I want to know what traffic my system can actually serve. And the reason for that is, let's assume you're building an application which is a photo sharing site. Can you guess which day of the year is going to have the most photo sharing? New Year's Eve. Imagine you're building an application which serves doorbells. Guess what day you have the most traffic? Anybody? Shout it out. Halloween. So you know that there's going to be unpredictable traffic in your application, but as an application developer, as an operator, one of the things you're concerned about is, when I have my spike in traffic, will DynamoDB be able to serve it? So customers have come to us and said, tell us how many partitions we have. But that's not really the right question to be asking. It is, what traffic can my table serve? So the way in which we told you to solve this problem was this really hokey thing, which requires a colored flowchart and all of this stuff. Is your table provision mode or on-demand mode? Let's assume it's on-demand mode. Then the first thing you have to do is switch it to provision mode. Then you have to set whatever the throughput is that you want to have. Now you can do that only one to the table or the index at any point in time. You can't do them both. And then when you're done, you have to lower the provision capacity to whatever you think it should be and then revert it to on-demand. All this is messy stuff. Customers have tried to do this. They've tried to do this for a table because Halloween is coming up or New Year's Eve is coming up. And then auto-scaling tried to kick in and auto-scaling got stuck and bad things happened. This whole thing was hokey. So last month, November, we launched a new capability called warm throughput. If you haven't looked at it, I strongly suggest you do. It consists of two things. An API to tell you what traffic your table can serve, table or index can serve, instantaneously. And the second, allow you to set that threshold. In the old days, you had to do this by actually raising the provision throughput. You don't have to do that anymore. You can just raise the warm throughput. We'll see how that works. Under the covers, we do the same thing. It's horizontal scaling. It's partitioning. But we gave you a couple of changes to the API. First, describe table will tell you what the warm throughput is. You can change the warm throughput with update table, or you can set it when you're creating the table. All right. So let's take some examples here. Now, this is the reason I like the SQL-ish syntax. Describe customers. And it gives you an output which says your warm throughput for this table is 12,000 RCUs, 4,000 WCUs. Thank you very much. And the table is active. Now, it turns out that create table has support for this, update table has support for this, and here's what those things look like. One of the things which, again, sorry for the commercial here for DynamoDB shell, when I started using DynamoDB, I had a hard time remembering the syntax for the API calls. So I made this little thing which was explain. Stick explain and some command up front, and it'll tell you what the API call is. So explain create table, primary key something, with a warm throughput of something, and oh, by the way, create a GSI for me as well. And all that is going to do, it's not going to actually create the table for you. It's going to tell you what you would have to do in the API, and oh, by the way, that's the API for you. Of course, you can actually create the table. In this particular example, I did not specify warm throughput for the index. You can do that as well. So now let's remove the explain and actually create the, or we created a table. I can alter a table, and I can set the warm throughput. Again, that's the API call you would make. So that's the explain up top. This is actually executing it below. It's going to do the alter, but unlike update table, which tries to do the update table like for a provision mode table, which tries to do it as quickly as possible, warm throughput might take a little bit of time. So here I'm raising it from 12,000 to 20,000. Yeah, maybe it takes 20 minutes. But the status will be updating. At this point, the index has a warm throughput, but the index is not, the warm throughput is not being changed. So the index status is active. Notice the difference here, updating, active. For those of you who remember what it was like with making a change to a table and an index, the provision capacity you could do one at a time. Here, you can do both. So you've got here a table, describe the table. The billing mode for the table is being updated, or the warm throughput for the table is being updated. The index is not being updated. I can go ahead and make a change to both. I can update both the warm throughput and the index at the same time. And you can do this in parallel with autoscaling, doing whatever it wants to do on a provision mode table as well. So the way in which we anticipate people would use this is, like many of our customers building applications at scale, you've got a capacity planning system, which says for Halloween, I expect to have a traffic of so many doorbell rings, or I expect for New Year's Eve to have so many photographs uploaded. Which means you know how many requests per second your table is going to take. Just make the call whenever you want. Make the call 2 weeks in advance. You're not actually raising the capacity on the table, you're only raising the warm throughput on the table. So if you were running in provision mode, you're not raising your provision capacity, you're just raising the warm throughput. If you're running in on-demand mode, you still pay only for the requests you're actually making to the table. All this is doing is, in the background, go do a bunch of splits. Because then when Halloween comes along and everybody starts pressing their doorbells, the table is just going to sail right along and do what it wants because you've already updated the warm throughput. Good so far? It's a whole lot easier than asking how many partitions you have and trying to multiply and do math, right? That's the reason we did this. Okay, so a couple of minutes, I told you 20 minutes later, we check again. Now they're both active with the new capacities. The table's been scaled up. When the traffic comes, it will be able to serve it. So try to show this graphically. Let's assume we have this. This is a load generator which we have, which tries to simulate traffic for testing. And here I had it generate traffic with 3 peaks per day, variable peaks and so on. And then I went and drew these orange lines, which are supposed to represent autoscaling kicking in. Autoscaling kicking in on a timed schedule. The table was provisioned, and the warm throughput was set at some 200 units. A user came along and said, you know what, I'm going to raise it to 300, performed an operation, raised it, or is that 350, raised it to 350. The warm throughput remains at 350. You keep doing your autoscaling changes here, no problem. They're completely independent operations. This is autoscaling, doing its thing. The blue is the traffic, and this is warm throughput. Now, this is the same thing with an on-demand table. It started off in this particular case with a warm throughput of about 270, I think was this illustration. This is an on-demand table. There's no autoscaling involved. What are you paying for? You're paying only for the requests you actually make. But the traffic spiked. The traffic went over the warm throughput number. What does DynamoDB do at that point? It splits. But it took a little bit of time for it to do the splits, and the warm throughput went up again, and it stayed there. You could have done this manually ahead of the spike, and you would not have had any throttling here. You would not have had any tail latency noticeably change here. You could have done this step earlier. Let's assume this is your Halloween traffic. you could have done the warm throughput raise here, go up. Your table is ready whenever you need it. So wherever possible, we would like you to move away from the old way of doing things. And by the way, if you're using CloudFormation or you're using, well, I know if you're using CloudFormation, warm throughput support is already available. We're working with the Terraform folks to get it in. Specify warm throughput when you create your table. Specify warm throughput when you're updating the tables. Automate it wherever you can. And the best thing is if you're using it for provision mode tables, you can do concurrent updates and it will not interfere with autoscaling. Let me know if that seems to make sense or, all right. I'll stick around after the presentation. If you have questions, we can talk about them. And for those of you who watched the keynote this morning, we announced support for multi-region strong consistency in global tables. So instead of talking about TTL, I figured more people would want to know how this worked. So let's start by talking about global tables. We've had global tables for a while. We launched global tables in 2017, but this was asynchronous global tables. In 2019, we launched a second version of asynchronous global tables, GT version 2. And you can have as many replicas of your table as you want. You can have it one in every region if you wanted. It's active-active. You can make writes in any region. We did conflict resolution based on the last writer. So if you had a table with replicas in 3 regions, and you made 2 writes, one in region 1, one in region 2, the later of the 2 writes is the one which would survive. One of the consequences of this architecture is that within the region, you have strong read after write guarantees. You do a consistent read, in the same region where you did the write, you will get it. But there is no read after write guarantees across regions. And the second, since replication is eventually consistent, it is possible that you do a write in region 1, and before that write makes its way over to the other regions, region 1 gets isolated. Now your data is in one region and one region only. It's possible. Network isolation happens. In that circumstance, if your application has to switch over to another region, your recovery point objective is greater than 0. This class of global tables is what we've had for a while. Try and show it to you in pictures. Here I have 5 regions, region 1, 2, 3, 4, 5. I do a write in the first region. Once the write is done, it's a regional write, which means it's written in 2 AZs. The third AZ is eventually consistently written, but then there's a replication to the other regions. So what happens if I do a write, and then I do an eventually consistent read in the same region? Well, this is a regional write, so it went to 2 AZs. It's possible that this EC read goes to the third AZ. And if it happens to go to the third AZ within a couple of milliseconds of this write, maybe you'll get old data. If you want strong read after write consistency guarantees, you must do a consistent read in region. This is how asynchronous global tables has always worked. Now suppose you do a write. Before the replication, you do a consistent read here. Well, the data hasn't made its way over, so there's no way you're going to see it. After the replication has happened, you do a consistent read here. Yes, you will get that data. It's a consistent read. The replication will guarantee a consistent read. This eventually consistent read here may not give you the latest data, because what is replication doing? It's doing a regional write, which means this write is written into 2 availability zones. If your eventually consistent read goes to the third one, maybe you're not going to get it. And okay, you did the replication before the write, you do an EC read, you're not going to get the data. This is async global tables as it exists today. And there's more examples. In the previous examples, I assumed that we were doing a write to a particular item, and we were reading the same item, the same primary key. Now let's take a slightly different example here. I'm writing to a particular partition key, or a particular primary key, and here I'm writing to the same primary key in another region. And time progresses to the right. This happens a little bit after that. So first thing which is going to happen is this write is a regional write. It's going to get replicated. This write is a regional write. It's going to get replicated. Since this was a later write, it is the one which is eventually going to survive. Eventually. But there's a brief period of time where this write will be replicated, the second one is not. While the state of the system will eventually converge, during the period of convergence, EC-read and C-read may give you old data, new data. In some cases, this is good enough for applications, but there's a lot of applications which said, we want strong consistency across regions. So, announced this morning, multi-region strong consistency for global tables. And here's a comparison of what it is. The writes are asynchronously replicated in both cases. Yes, that is not a typo. The writes are asynchronously replicated, but while the eventual state is deterministic, you now have universal write ordering at the key level. And you have global read after write consistency. Consider the case where you have an application where you want to generate unique sequence numbers globally. Well, strongly consistent global tables will give you the ability to do that. Two regions will never generate the same sequence number, and you will have dense sequence numbers if you so desire. You can do that. So, multi-region strong consistency is a mouthful. MRSC is a little bit easier to pronounce. I'm just going to call it MERCY. If you built applications with asynchronous global tables, you'll realize it's really merciful to have this one. So, MERCY global tables. And here's how it works. One thing to remember, eventually consistent asynchronous global tables, you can have as many replicas as you want. MERCY global tables, at this point, you can have 3 regional copies. 3. We're going to change that. Not at this point, it is 3. And the way in which we implemented it, we added this new construct at the bottom. It's a multi-region log. You'll hear it as MRJ or multi-region journal. If you're going to the presentations about DSQL, you'll hear about the same construct. This multi-region log is a multi-region strictly ordered append-only log. So the way in which we use it, you do a write in the first region. That write is first published to the journal. When the journal sends callbacks to the regions, the callback here triggers your 200. So you do a write. The first thing we do is try to send it to the journal. The journal callback triggers your 200. And at the same time, the callback will go to the other regions. You remember I said the writes are sent asynchronously. This is that asynchronous behavior. The write goes from the originating region to the log to the 3 regions. Okay. And you get your 200 there, and you're off to the races. That's the asynchronous nature which you should remember. Okay. So what actually happens within the journal? We have journal in multiple regions, the same 3 regions. As soon as the data is in 2 of the regions, the log will say, okay, the write is now durably recorded in 2 regions. Let's assume that before this write to the 3rd region happens, one of these regions goes offline. The data is in another region. This is the reason we can give you a RPO0 on single region isolation. So data is durably written in 2 regions. The callback happens. The 3rd one is eventually written. And you get your 200 over there. Now, this is a regular regional write. What's a regional write? Write to 2 AZs. As soon as it's done in 2 AZs, it's good. So what's that look like? The write starts in the second AZ of region 1, written to the log. The callback comes here. It's written to 2 AZs, and then you get your 200, and then lazily to the third. Okay. I did say that you have global read after write consistency, so we have to still deal with that. So now let's talk first about EC reads. I do a write to a table. It's a strongly consistent global table, and then I do an EC read. Is it guaranteed that I will get the latest data? No, this is a regional write. You may go to the third AZ, which doesn't have the data yet. So that could give you stale data. At this point, you might wonder, what's the point in this whole log? I told you it gives you strictly in-ordered writes. So let's assume that writes were sent to the log in the order A, B, C. What we guarantee is that the callbacks in the regions is going to be in exactly the same order, A followed by A, then B, then C. The amount of time between them may be different, but the order is guaranteed to be the same. It's a append-only, strongly ordered log. That's what this thing gives you. So how are we going to use that to give you strong cross-region read after write consistency? Well, let's introduce a new concept, that little thing there, the heartbeat. So I do a write. It goes to the log. There are callbacks. You get a 200. You're done. When you do a consistent read, in order to serve this consistent read, the region needs to know that it's completely caught up. So it sends a heartbeat over to the log. A heartbeat is a message which is not durably persisted here, but it does generate a callback. So when the consistent read heartbeat is received here, the region knows it's got everything. So it can serve the 200 here. This is where the strong ordering is a value, because it's guaranteed that this write will be before the heartbeat. The write is before the heartbeat. Okay, so let's start with a slightly more difficult example. I do a write, the write goes over to the log. There are callbacks. So the write is done in all 3 regions. Okay, this is easy. In a different region, for the same key, there's another write. That region generates a log. The order is A, then B. Therefore, the callbacks must be in the same region, in the same order. But before the callbacks happen, somebody up here does a consistent read. The callbacks for this are not yet done. There's a consistent read. So in order, you have a write, a second write, and a consistent read. So how is the journal going to help us? You got the write here, you got the second write. They're guaranteed to be in order. The callbacks are guaranteed to be in order. The consistent read generates a heartbeat, which is not persisted in the log, but when the heartbeat response shows up, the region knows it's caught up. It can serve the consistent read. Therefore, it is guaranteed that this consistent read here will include write B. Strong read after write guarantees across regions. Okay? So after that, another write comes along, same. That write goes into the log, and you notice the order in which the writes happened in the log is exactly the order in which they will be manifested in each region. The timing might be slightly different. They're asynchronous. But we guarantee strong cross-region read after write guarantees with heartbeats. Earlier in the presentation, I told you, where possible, do things asynchronously. If you want predictable latency at any scale, do things asynchronously. This is asynchronous writes, but the guarantee is the ordering. That's the thing which gives you the strong read after write guarantees. Okay. One more example. I think this is the last of the examples. You do a write, you do a consistent read in a different region. Again, the heartbeat guarantees that the region is caught up, and therefore it can serve the consistent read. Therefore, this consistent read is guaranteed to include everything before that point in time, which means this write is reflected. The write is reflected here. Okay. If I do a consistent read here, before the write, again, we generate a heartbeat. The ordering guarantee here says the done will be before the heartbeat. Therefore, this consistent read has this write, even though it was not written to the region. The order you have things recorded in the log is the order in which you have them in each region. So, we built multi-region strong consistency based on multi-region journal. This is a new internal construct which we use. It is an append-only log which provides strict ordering. Now, the place where we expect that customers are going to use this is where they want the strong multi-region consistency guarantees. At this point, you will have 3 replicas for these tables. When you do a write in any region and you receive success, it is guaranteed that your data is durably recorded in 2 regions. Maybe in the log in 2 regions, but it is durably in 2 regions. It will asynchronously be written to your tables. But if one of the regions were isolated, your RPO guarantee is still 0. So those of you who are building applications with financial transactions, you might want to use this for some parts of your application. And you get strong consistency guarantees guaranteed globally if you do a consistent read. Strong read after write consistency globally. So that's, at a very high level, the way we built strongly consistent global tables. There is another session, I believe the number is DAT406. If you want to hear a whole hour about strongly consistent global tables and how we expect people are going to use it, you should go to that session. So we do these presentations, like I said, every year to share with you some of our learnings and hopefully help you build applications which can leverage the same predictable low latency guarantees which we provide. These are some presentations from past years. The first one is one which I watched before I joined AWS, and these are presentations which I've done, this one with Alex and this one last year. There are other presentations about DynamoDB which you might also find interesting. Here's a list of the ones at this reInvent, and in case you want to search for them in the catalog, you should be able to find them. So thank you all very much for coming here. I know that you have a choice of many sessions you could possibly have attended. So thank you for being here, and please take a minute to fill the feedback form.